Chapter 4 Structure of the Atom. Charged particles in matter. Matter is made of atoms and molecules. Atoms of one element are different from the atoms of another element. Different atoms combine together to form different substances. It was earlier believed that atoms are indivisible, but now we know that atoms are divisible and that atoms have an inner structure. The phenomenon of static electricity hinted at the presence of particles in matter. In our day-to-day life, there are certain actions that make us aware of the electrifying effect caused between two different materials. For example, run a comb through your dry hair and bring it near bits of paper. Wow! They get attached to your comb. What made this happen? Well, it happens due to static electricity. Let us perform an activity to understand what static electricity is. Take a glass rod and rub it over a piece of silk cloth. When this glass rod is brought near bits of paper, they are attracted towards it. The glass rod attracts the small pieces of paper because it gets charged and develops positive electric charge on it. The silk cloth also develops a negative electric charge simultaneously. These charges are static in nature. That is, they do not move from one object to the other and are thus called static electric charge. Where does this charge come from? This charge comes from the atoms present within the comb and glass rod. These activities show that some charged particles are present in matter and that atoms are divisible. Discovery of the electron.
In 1897, an English chemist, J. Thomson, conducted some experiments on the structure of an atom. Thomson discovered that there existed some particles in an atom. He carried out his experiments using a cathode ray tube.
A cathode ray tube is a glass tube that can contain a gas at very low temperature.
There are two metal plates at the two ends of the tube. The metal plate connected to the negative terminal of a battery is the cathode, while the metal plate connected to the positive terminal is the anode. Thomson observed that when a high voltage was applied between the two metal plates of the cathode ray tube, the cathode emitted rays. These rays were called cathode rays, and they consisted of a stream of particles, which were found to possess negative electrical charge and were called electrons. These particles were about 1,800 times lighter than hydrogen.
Electrons are present in the atoms of all the elements. An electron is denoted by the letter E. Its mass is considered to be negligible and its charge is -1.
The discovery of electrons indicated that atoms were not indivisible. After the discovery of electrons, scientists thought that atoms had some internal structure.
Discovery of the proton. E. Goldstein in 1886 performed an experiment using a discharge tube having a perforated cathode and an anode. When a high electrical voltage was passed through a gas at a very low pressure taken in the discharge tube, some rays were produced at the anode. They were called as anode rays or canal rays. These rays consisted of positively charged particles. The formation of positively charged rays led to the discovery of another subatomic particle, the proton. Protons are represented by the symbol P positive. The mass of a proton is about 1,840 times the mass of an electron. The mass of a proton is taken as 1 unit. A proton has +1 charge. Protons are present in the atoms of all the elements.
Discovery of the neutron. In 1932, James Chadwick discovered another subatomic particle inside the atom. This particle had no charge and had a mass nearly equal to that of a proton. It was present in the nucleus along with the proton. He named it as neutron. A neutron is represented as N. Neutrons are present in the nucleus of all the atoms except hydrogen.
The structure of an atom. Dalton's contribution.
In 1808 AD, Dalton, a British chemist, provided his basic theory about the nature of matter. According to his theory, all matter is made up of very small particles called atoms. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. But the discovery of two fundamental particles, protons and electrons, inside the atom led to the failure of this aspect of Dalton's atomic theory. Scientists proposed various theories to explain the structure of an atom. Based on their theories, they proposed various atomic models. A British physicist, J. Thomson, was the first scientist to propose a model for the structure of the atom.
Thomson's model of an atom.
Thomson proposed a model of an atom to be similar to a plum pudding. He proposed that an atom consists of a positively charged sphere where the electrons are embedded in it. The positive and negative charges are equal in magnitude. So, the atom as a whole is electrically neutral. But his model could not explain the results of experiments carried out by other scientists like Rutherford and Bohr.
Rutherford's model of the atom.
Rutherford overturned Thomson's atomic model by his gold foil experiment. His experiment demonstrated that the atom has a tiny, massive nucleus. It thus rejected Thomson's model of the atom. Rutherford's scattering experiment. Rutherford selected a gold foil as he wanted a very thin layer. In his experiment, fast-moving alpha particles were made to fall on a thin gold foil. Alpha particles are helium ions with +2 charge and have a considerable amount of energy. These particles were studied by means of flashes of light they produced on striking a zinc sulfide screen. He expected the alpha particles to pass through the gold foil with little deflections and strike the fluorescent screen. But the observations he made were quite unexpected. He observed that most of the alpha particles passed straight through the gold foil. Some were deflected through small angles, and some were deflected through large angles. Very few appeared to bounce back. From the experiment, he concluded that since most of the alpha particles passed through the gold foil without getting deflected, so most of the space inside the atom was empty. Very few particles deflected from their path. This indicated that the positive charge of the atom occupies very little space. A small fraction of alpha particles bounced back by 180 degrees. This indicated that the entire positive charge and mass of the atom was concentrated in a very small volume within the atom. Let us perform an activity to understand Rutherford's experiment. Stand near a barbed wire fence and throw marbles towards the fence, one after the other in quick succession. What do you observe? Most of the marbles pass through the gaps in the wires of the fence to the other side, while a few of them hit the wire and get deflected by large angles or bounce back. This activity provides an explanation to understand Rutherford's experiment. It suggests that the fact that most alpha particles pass through the gold sheet proves that atom consists mainly of empty space. Small number of rays bounced back as if they hit a solid object. The part from which the positively charged alpha particles are turned back is positively charged and is very small in size as compared to the empty space. Based on Rutherford's observations, he formulated his theory of atom. The main features of his theory are as follows. There is a positively charged center in the atom called the nucleus, in which nearly all the mass of the atom is concentrated. Negatively charged particles, called electrons, revolve around the nucleus in paths called orbits. The size of the nucleus is very small as compared to the size of the atom. His model can be compared to the solar system, where the planets are compared with electrons and the sun with the nucleus.
It is called the nuclear model of the atom.
What were the drawbacks of Rutherford's model of the atom? Rutherford's atomic model could not explain how the moving electrons could remain in its orbit. Any charged particle during acceleration would give out energy, and while revolving, it would lose energy and eventually fall into the nucleus. This means that the atom would be highly unstable. But matter is composed of stable atoms. Thus, the major drawback of Rutherford's atomic model was that it could not explain the stability of atoms.
Niels Bohr's atomic model.
Niels Bohr revised Rutherford's atomic model and put forth the following suggestions. Electrons were confined to clearly defined orbits. Electrons do not radiate energy while revolving in the orbit. They could jump between orbits, but could not freely spiral inward or outward in intermediate states. An electron must absorb or emit specific amounts of energy to transition between these fixed orbits. Distribution of electrons in orbits. According to Bohr's model, electrons occupy certain stable orbits or shells. Each shell has definite energy. These orbits or shells are represented by the letters K, L, M, N, or the numbers 1, 2, 3, 4. The maximum number of electrons present in the shell is given by the formula 2n square, where n is the orbit number or shell number. The maximum number of electrons in different shells are as follows. The first orbit or K shell will have 2 multiplied by 1 square, that is 2 electrons. The second shell will have 2 multiplied by 2 square, that is 8 electrons. The third shell will have 2 multiplied by 3 square, that is 18 electrons, and the fourth shell will have 2 multiplied by 4 square, that is 32 electrons, and so on. The maximum number of electrons that can be accommodated in the outermost orbit is 8. The orbits or shells are filled in a stepwise manner. Electrons are not accommodated in a given shell unless the inner shells are filled. Electronic configuration of elements. The energy of every electron depends upon the shell that it occupies. Electrons in the K shell have minimum energy. Electrons in subsequent shells have higher energies. The arrangement of electrons of each element is called the electronic configuration of the element. It is represented by numbers which correspond to the electrons in the shells. Let us study the electronic configuration of some elements. We shall start with hydrogen. The symbol of hydrogen is H. The number of electron is 1. Therefore, the electronic configuration is also 1. Since it has only 1 electron, it will occupy the K shell. The next element is helium. Its symbol is He. It has 2 electrons. The electronic configuration is also 2. Both these electrons will occupy the K shell. Next is lithium. Its symbol is Li. The number of electrons is 3. Therefore, the electronic configuration is 2, 1. This means that there are 2 electrons in the K shell and 1 electron in the L shell. Next is carbon. Its symbol is denoted by capital letter C. The number of electrons is 6. Therefore, the electronic configuration is 2, 4. This means that there are 2 electrons in the K shell and 4 electrons in the L shell. Next is nitrogen. N. The number of electrons is 7. Therefore, the electronic configuration is 2, 5. This means 5 electrons are in the L shell. Similarly, the electronic configuration of oxygen is 2, 6. This means that there are 6 electrons in the L shell. Next is fluorine. There are 7 electrons in the L shell. The electronic configuration of neon is 2, 8. This means that there are 2 electrons in the K shell and 8 electrons in the L shell. Next is sodium. The number of electrons is 11. There are 2 electrons in the K shell, 8 electrons in the L shell, and 1 electron in the M shell. Therefore, the electronic configuration is 2, 8, 1. Next is chlorine. The number of electrons is 17. This means that there are 2 electrons in the K shell, 8 electrons in the L shell, and 7 electrons in the M shell. Therefore, the electronic configuration is 2, 8, 7. Next is argon. Its symbol is denoted by Ar. The number of electrons is 18. This means that there are 2 electrons in the K shell, 8 electrons in the L shell, and 8 electrons in the M shell. Therefore, the electronic configuration is 2, 8, 8.
Valency. We know that electrons are arranged in different shells or orbits. According to Bohr's scheme of distribution of electrons, the outermost shell of an atom can accommodate a maximum of 8 electrons. The electrons present in the outermost shells are called the valence electrons. Atoms of elements having a completely filled outermost shell are stable and are chemically unreactive. The atoms of elements like helium, neon, argon, krypton, xenon, and radon have completely filled outermost shells, thus they are stable and chemically inert. Helium has 2 electrons in its outermost shell, and the other inert gases have 8 electrons in the outermost shell of their atoms. The outermost electrons of inert gases do not take part in any chemical reaction. Atoms of other elements combine with one another to achieve the inert gas electronic configuration and become more stable. This combining capacity of an element is called the valency of the element. When the atoms combine to form a chemical compound, they do so in such a way that each atom gets 8 electrons in its outermost shell or 2 electrons in the outermost K shell. Atoms can achieve the inert gas electronic configuration either by losing 1 or more electrons or by gaining 1 or more electrons or sharing 1 or more electrons. Let us study some examples. The atomic number of sodium is 11. So, its electronic configuration is 2, 8 and 1. It has 1 electron in its outermost shell. Sodium atom tends to lose that electron to form a positively charged sodium ion, having an inert gas configuration 2, 8. Since sodium atom loses one electron to achieve the inert gas electronic configuration, the valency of sodium is 1. The atomic number of chlorine is 17. So, its electronic configuration is 2, 8 and 7. It has 7 electrons in its outermost shell. Chlorine atom accepts one electron to form a negatively charged chloride ion having an inert gas configuration 2, 8, 8. Since chlorine atom accepts one electron to achieve the inert gas electronic configuration, the valency of chlorine is 1. What is the valency of hydrogen? The atomic number of hydrogen is 1. The hydrogen atom has a single electron in its outermost orbit. It requires only one electron to complete the duplet. Thus, its valency is 1. Hydrogen atom shows a tendency to share its electron to attain a stable electronic configuration. What is the valency of nitrogen? The atomic number of nitrogen is 7. So, its electronic configuration is 2, 5. The nitrogen atom requires 3 electrons to complete its octet. Thus, its valency is 3. What are the valencies of the elements given below? Carbon, electronic configuration 2, 4. Magnesium, electronic configuration 2, 8, 2. Oxygen, electronic configuration 2, 6. The electronic configuration of carbon is 2, 4. Carbon has 4 electrons in its outermost orbit. Carbon requires 4 electrons to complete its octet. A carbon atom can share these 4 electrons with 4 electrons of other atoms to attain a stable electronic configuration. Hence, its valency is 4. The electronic configuration of magnesium is 2, 8, 2. Magnesium has 2 electrons in its outermost shell. Magnesium can lose these 2 outermost electrons to attain a stable electronic configuration. Hence, its valency is 2. The electronic configuration of oxygen is 2, 6. Oxygen has 6 electrons in its outermost shell. Oxygen requires 2 electrons to complete its octet. Hence, its valency is 2. Atomic number and mass number.
The nucleus of an atom consists of protons and neutrons. Atomic number of an element is the number of protons present in the nucleus. It is denoted by the capital letter Z. For example, hydrogen has 1 proton in its nucleus. So, the atomic number of hydrogen is 1. We express it as Z is equal to 1. The number of protons and electrons in an atom are equal. Thus, the atom of an element is electrically neutral. How many electrons are present in the atom of carbon? The atomic number of carbon is 6. Means the number of protons in the nucleus is 6. We know the number of protons and electrons are equal. So, the number of electrons present in the atom of carbon is 6. What is its atomic number? Since the number of protons and electrons are equal, the atomic number of sodium is also 11. Atomic mass number of an atom is different from the atomic number. The total number of protons and neutrons present in the nucleus of an atom is called the atomic mass number or only mass number of the element. It is denoted by the symbol A. The atomic number Z, the atomic mass number A, and the symbol of an element can be represented as shown. The mass number A is written as the superscript and Z is written as the subscript. For example, sodium has atomic number 11 and atomic mass number is 23. Therefore, it is represented as Na1123. Let us take another example. The atomic number of calcium is 20 and its atomic mass number is 40. How many neutrons are present in the nucleus of calcium? Here, atomic mass number A is equal to 40 and atomic number Z is equal to 20. So, the number of neutrons is A minus Z. This is equal to 20.
Isotopes and isobars. Isotopes.
We know that the number of protons is the same for all the atoms in an element. Is it true for neutrons too? No. In nature, there exist some elements which have atoms with different number of neutrons. Such atoms of the same element are called isotopes. For example, chlorine exists in nature in two isotopic forms, one with mass number 35 and another with mass number 37. Many elements consist of a mixture of isotopes. For example, hydrogen has 3 isotopes. They are hydrogen, deuterium, tritium. Ordinary hydrogen has no neutron in its nucleus, but deuterium has 1 neutron and tritium has 2 neutrons in the nucleus. Let us take another example, carbon. Carbon has 2 isotopes, C612 and C614. The isotopes of an element have the same chemical properties, but some physical properties may be different. Why? Isotopes of an element have the same atomic number, and thus they have the same number of electrons. The chemical property of an element depends on electrons only, not on neutrons. The proportions of isotopes are often called their relative abundances. For example, the element chlorine has 2 isotopes, chlorine 35 and chlorine 37. The relative abundances of these 2 isotopes of chlorine are 3:1. In any compound containing chlorine, the ratio of the 2 isotopes is always 3:1. We know that chlorine occurs in various compounds. Chlorine atom could be in chlorine gas, in hydrochloric acid, or in sodium chloride, or any other compound of chlorine. In all these compounds, for every 3 chlorine 35 atoms, there is 1 chlorine 37 atom. When we determine atomic mass of chlorine, by chemical method, we find that it is the average of the atomic masses of the two isotopes. The average atomic mass of chlorine can be calculated theoretically by a general method as follows. Suppose that an element has two isotopes with the relative abundances A1 and A2 and atomic masses M1 and M2. Then the average atomic mass Ma equals to the sum of the product of A1 and M1 and A2 and M2 divided by the sum of A1 and A2. We have already discussed that chlorine has two isotopes, chlorine 35 and chlorine 37, with the relative abundances in the ratio of 3:1. The average atomic mass of chlorine is calculated as follows. The average atomic mass of chlorine, that is Ma, equals to the sum of the product of 3 and 35 and product of 1 and 37 divided by the sum of 3 and 1. This equals to the sum of 105 and 37 divided by 4. This equals to 35.5. Thus, the average atomic mass of chlorine is 35.5. What are the uses of isotopes? It is interesting to know that the isotopes of some elements have special properties, and so we use them in various applications. Uranium-235 is used for nuclear fission and as a fuel in nuclear reactors. An isotope of cobalt is used in the treatment of cancer. An isotope of iodine is used in the treatment of goiter.
Isobars.
Potassium K atom has 19 protons and 21 neutrons in its nucleus. Calcium Ca atom has 20 protons and 20 neutrons in its nucleus. Argon Ar atom contains 18 protons and 22 neutrons. What are the atomic mass numbers of potassium, calcium, and argon? The atomic mass numbers of each of these elements can be determined by adding the number of protons and neutrons. The atomic mass number of potassium is 19 plus 21. That is 40. The atomic mass number of calcium is 20 plus 20. That is 40. The atomic mass number of argon is 18 plus 22. That is 40. Thus, the atomic mass numbers of each of these elements is 40. In the above examples of potassium, calcium, and argon, we see that the atomic mass numbers are the same. Since the number of protons in each of these elements is different, the number of electrons are also different. Atoms of different elements with different atomic numbers, but which have the same atomic mass numbers are called isobars.